How long will it take me to get all of these buttons pressed?
Well, I just discovered rather horrifically that I also have the ability to stop a
Hold on.
broadcast.
There you go. Couldn't hear you. Now I can hear you.
I said I also just discovered rather horrifically that I also have the ability to stop broadcast, and I almost did because I went orange button. That means
I know, isn't it? So many times. Have you ever actually stopped a broadcast when you went to start it?
Not yet, but I've failed to start broadcasts thought were started before. So
yeah, no, I will like go after a whole bunch of buttons. Or like I got to press unmute and I got to turn Pamela's video feed on, and there's the stop broadcast button. I'll press that one.
Yeah. There are too many buttons.
Yeah, absolutely. And yet here we are, cranking away another episode of Astronomy Cast.
Yes.
So this is going to be the end of our run on planetary exploration, planetary search and discovery, extrasolar planets.
Until someone creates a kick-ass coronagraph, then we'll be back.
Right, then we'll be back, yeah. And we're going to start a new series.
That was suggested by someone whose name is not in my head at the moment, who is truly awesome and we're really grateful for, who suggested we should do a series on great experiments that helped us get to where we are today.
I think we're still kind of formulating our plan on how we're going to put this together. Will we, there you go, it's Rachel Roberts.
Okay, thank you, Rachel.
So we're gonna like whether we're like a bunch of really cool experiments about gravity, and we can talk about a bunch of cool experiments about the milligram drop experiment and things like that, right? And so whether we'll bundle them up, whether we'll separate them into separate episodes, I'm not really sure because we'll need to discuss it. But I think it's a great, we always go into the how we know what we know, and what Rachel suggested, which was just terrific, was like just go delve all the way down and like talk about the experiment and how it was constructed and how they ran it and what the outcome was. So I think it's a terrific idea, and we will do it.
Yep.
I love it. So that's going to start next week. Anything else? If you have no idea what it is that you have stumbled into, you're watching a live recording of our weekly Astronomy Cast podcast. This will be episode 367, Spitzer Does Exoplanets. We'll take about half an hour to record our episode, and then we'll stick around and we'll answer some of your questions about space and astronomy. I can't stick around too long. I got to go out for lunch with my dad, who's in town. So. Dad, if you're listening to this, lunch was fun. Which he does. He listens to the podcast. So I'm going to say hello to Michael Jobin, Richard Clark, James Oliver, Gazelle Severin, Michael Mayer, Nancy Graziano, Ed Thompson, Tony Lynch, Guido Bibra, Margin Panic, Thomas Tranneker.
There's someone named Margin Panic?
I know. Yeah, Marjan.
I heard something that sounded more like the lady that yelled at us about our dissertations.
So, hey, everybody. I'm really glad to have you all here. Okay. Are you ready?
No. Sorry.
Should I just do this some more? If you want to ask us some questions, you can go ahead and join the conversation. You just have to click the button wherever you're watching this video, and you'll see the Q&A app, and you can go ahead and post whatever you want in there. As Nancy is always great for mentioning, just remember that this is more for the Q&A, because seriously, if you guys ask a lot of questions and there's a lot of chit-chat, I have a really hard problem finding the questions. So just straight up questions in the Q&A app, and then feel free to have the chit chat over on the event page, and then also talk on Twitter too at the same time, because I think that's sort of what we need to do in our sort of future broken up lives here.
So I apparently need to go close a bazillion doors because there's a dude with a leaf blower that didn't understand he should have had that done in November.
Is that happening right now?
Yes, and I need to banish the dogs who are barking at the leaf blower dude. So banishment.
Okay, well then I will just continue. Let's see. I'm going to use this opportunity to let everyone know that there's a great community on Google Plus that you should totally join. There's two. One is the Google Space community, which is monstrous. 300,000 people, I think. But then the other one you should join is the WSH crew, and this is the crew that's come together to talk about the stories we do on the Weekly Space Hangout, and they have become a real family. And although there's only about 300 people there, they're really hardcore, really close, tight-knit, and I highly recommend that community, as well as the CosmoQuest community, which was the one that we put together from the Bad Astronomy Universe Today community. So you should go totally join that. What else can you do? Are you back?
I am back,
Right.
and hopefully there's enough dogs between me and enough doors between me and the dogs.
Okay, awesome.
Leaf blowing should not happen in February.
You should see our videos. We have every kind of animal and two-stroke engine has tried to get into one of our videos. So we've had ravens, we've had dogs, we've had seagulls, eagles, leaf blowers, people with like two-stroke, I don't know, like little like mopeds and things like that. It's just hilarious. Yeah, like if you're attempting to record audio or video, count on getting some kind of noise disturbance.
Oh yeah, we've tried filming some episodes of the universe at the City Museum in St. Louis, and the City Museum folks are great, but inevitably the day we're filming, there's like a school group at a weird hour that we weren't anticipating, and yeah.
I actually recorded Friday's episode of the Weekly Space Hangout. It was a holiday, and the kids were just everywhere, and it was hard to kind of keep them out of the sight, out of mind. Oh, and we had Ron Guerin on Friday's Weekly Space Hangout, the astronaut.
That's awesome.
It was amazing. So if you haven't already had a chance to check that out, please do. We've got Paul Glister as our guest this week, so from Centauri Dreams, and we're going to try and put a cool new guest every week for the Weekly Space Hangout. So.
That's awesome.
To Susie Murph for helping organize these. All right, now can we do a show?
Yes. Sorry. Fail.
Okay. No, I'm ready.
I'm pressing record.
I have also pressed record.
And it's recording, which is so exciting.
Okay.
Hello, Preston.
Here we go. Astronomy Cast, episode 367. Spitzer does exoplanets. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today. With me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. I want to shamelessly self-promote something this week.
This is unusual in what way?
What are you kidding me? No.
I adore you. I just remember when your Phases of the Moon app came out, which is an awesome app, but you use that sentence a lot.
Yeah. So I'm now going to shamelessly self-promote my Patreon campaign. So you can go to patreon.com/universetoday, and you can kick us a couple of bucks every month, and that goes for making Universe Today. We remove all the ads from Universe Today from you. You get advance access to all the cool videos that we're doing. I'll follow you on Twitter. We shout out in the videos that we record your name, and seriously, it makes a huge difference. Ads suck, and being a way that we can actually just work directly for the fans who love the stuff that we do, that means the world to us. And so this is the future. I think it's just fantastic for all the people. I really want to thank all the people that have already supported me, and I would love it if you can kick a couple of bucks our way. And
after you kick a couple of bucks to him, you need to also go sponsor the Patreon campaign for Learning Space, because we use Patreon to fund all of our teacher professional development. So you can help pay the salaries of Nicole Bracey and Nicole Gallucci, whose name I finally know how to pronounce. Nice. And they will turn your money into helping teachers get science into the classroom. We will not follow you on Twitter. We will instead educate the world. It's a different priority, but we can keep up better with teachers than with Twitter.
And we are going to be doing a Patreon campaign for Astronomy Cast shortly. So stay tuned for that. And all hail Patreon.
Yes.
If you're a creator,
Cole Palmer, if you're listening, thank you.
Yeah, absolutely. All right, let's get rolling with the show today. So we spent the last few weeks talking about different ways that astronomers are searching for exoplanets. But now we reach the most exciting part of the story, actually imaging these planets directly. And today, we're going to talk about the work that NASA's Spitzer Space Telescope has done viewing the atmospheres of distant planets. All right, Pamela, so we've talked about Spitzer a bunch of times. We've talked about Spitzer in terms of just infrared astronomy. We talked about the actual, just the telescope and what happened with the telescope. But let's really focus in on Spitzer's work for observing extrasolar planets, and then maybe what the future holds for this method of looking at the atmospheres of planets.
So I'd like to start by clarifying that when we say directly imaging exoplanets, what we mean is getting spectrum of their atmospheres. So Spitzer is allowing us to directly detect the characteristics of exoplanets, from wind speeds to what their atmospheres are composed of, but we can't look at a planet and say it's blue or it's green. So
that's what I said. That's exactly what I said.
The Spitzer Space Telescope launched back in 2003. We did an entire episode on the dude it's named after. We did an entire episode on it. And it was originally designed to see very red waves of light, the far infrared. And to do that, it needed liquid helium on board. And as it was designed to do, over time, it used up all of that liquid helium. And in May 2009, this glorious space telescope warmed up. But it only warmed up so far as it can still see into the infrared, just not as far into the infrared. And because they were planning for this to happen, they designed a spacecraft with instruments that can still work now that it's a little bit warmer. And some of those detectors include spectrographs that are capable of detecting atomic and molecular lines from other stars and apparently other planets.
And last episode, we talked all about spectroscopic lines and how a spectrograph is laid out, and how you build a room that you display the rainbow of the light from a star. Spitzer doesn't have a room to do this, so what is the instrument like on Spitzer?
Well, so different types of spectrographs have different purposes. The ones that we were talking about last week are extraordinarily high resolution in order to determine exactly how fast a star is or is not moving. This means that when we look at its lines, we can, using spectrographs like that, if there's two different versions of the same atom side by side, for instance, different versions of lithium, we can see those differences. If there are two different versions of a molecule, like different versions of magnesium hydride, which I've studied in the past with a Coude spectrograph, we can see those different versions. That high resolution is what allows us to see littler planets yanking around on little stars, and big planets yanking around on big stars, and everything in between. But once we know there's a planet there, we can do something else. We can also start trying to separate out the light from the star and the light from the planet. And telescopes like the one that is used at Lucille for HARPS, they don't really do that so much, because the light from the star, as seen in optical, just totally drowns out the light from the planet. But with Spitzer, looking in the infrared, planets, they're really good at absorbing heat and re-radiating it in a variety of different ways, and stars aren't usually quite as bright out in the infrared as they are in the, bluer wavelengths of light. So with Spitzer, we have this fabulous combination of, we're looking in the colors that planets are brightest and stars are fainter, and this allows us to start to make out the light of the planet entwined with the light of the star.
It's weird to think about that idea that the star is less bright. You know what I mean, right? Like, because you just imagine if it's like a bright star, it's just going to overpower everything that we see because of its sunlight and because of its visible light. But I mean, obviously, stars do radiate in the infrared as well, but they're pushing a lot of that into the visible light, into the X-rays, and so on. And so it's actually quite funny that you can sort of split the difference between the brightness of the planet and the brightness of the star when you push into that infrared spectrum.
And this all goes back to, again, we did an entire episode on this, it goes into black body radiation. The color of light where an object gives off the most light is directly related to the temperature of that object. So this is partially why really hot stars are bluer and really cold stars are redder. Those wavelengths are where the peak intensity from the stars are. Now with the black body intensity, it's kind of like you taper off towards zero, going towards longer and shorter wavelengths, and you have this beautiful asymmetric curve. We take advantage of that curve when we use the Spitzer Space Telescope. And we also take advantage of transiting planets. So you do have to have not necessarily a planet that passes directly in front of the star, but you need a planet that passes directly behind the star.
Whoa. It's like the opposite of a transit. It's like the opposite. What do they, what do they call it when the star eclipsing? What do they call it when the star is going in front of the
planet has been eclipsed by the star?
Has been or an occultation?
Sort of, kind of.
Yeah, like no, I guess not. When a moon passes in front of the star, that's an occultation. Anyway, so can you explain that then? So let's explain that. Why when the planet passes behind the star, can we tell what the planet's atmosphere is?
Well, it's because we have to do subtraction. And what we really need is that clean spectra of the star. We can observe the combined light of the planet and the star, even if the planet isn't directly in front of the star. So if they're side by side, as long as that planet is radiating both heat emission from, well, it absorbs it, it's now giving it off like Jupiter does. Jupiter gives off more energy than it receives from the sun. So you have a nice hot Jupiter, it's giving off more light than it's receiving, and it's heated up anyways, so we have a nice, really warm object. Stick that right next to the star or in front of the star, and you now have the combined spectra of planet plus star. Now, we unfortunately aren't in the situation where we can readily just go, let's erase the star by looking strictly at the planet. That requires a coronagraph. As we've discussed, we don't really have super awesome coronagraphs yet. We're getting there. There's a few good ones. We have some direct images of planets, but not good ones. So Spitzer doesn't have a coronagraph, and so the best we can do is wait for that planet to duck behind Spitzer, not Spitzer, to duck behind the star. Sorry about that. And when the planet is behind the star, we're not seeing any of its light. We get a clean spectra of just the star. We now take the spectra of star plus planet, subtract spectra of star, we are left with spectra of planet.
So what's the process then? How do the astronomers choose which objects to point at? How do they know there's going to be a planet there to observe?
Well, they're either looking at something where we already know there's a planet via the transit method, or it's a survey object. A large number of scientists have said, I'm going to search, and this is why we originally started getting into this game with objects like 51 Peg and the Cygnus binary system. I'm going to look at sun-like stars, or at least stars that are very high in metals. Metals make planets. And I'm just going to look at them with the Doppler method to look for the wiggles that are related to a planet being there. Add in transit surveys, we have Crow, we have Kepler. Throw those in, throw in the random person in their driveway with their 4-inch reflector or refractor getting lucky with awesome photometry, and we've started to find planet after planet after planet. Now, we're not in general going to do that sort of survey work using a space telescope, but once planets have been identified via some other means, we can start doing follow-up observations with Spitzer. Now, there's also scientifically interesting objects that they're going to be doing high-resolution spectroscopy of. And occasionally we get into really lucky situations where we knew there was one planet that we'd found via some method. And then once we start subtracting that star off, we realize, wait, there's other things there as well.
Right. So, I mean, so they typically identify the targets using some other method, be it, they use the transit method, the rate of velocity method. People find them from the ground. They find this candidate, and then I guess if it meets a certain kind of criteria, they think, okay, this is the kind of thing that we can observe with Spitzer.
So ideally what they're going to start by chasing is the HotJupiters. These are the objects that are, well, like their name says, gas giants similar to Jupiter. But the hot part means that quite often they're in orbits that are far smaller than the orbit of even Mercury. So you're looking at a Jupiter-like object snuggled up so closely to its sun that in some cases it actually raises tidal forces, waves on the surface of both the star and the planet.
Got it. And so what kinds of planets then has Spitzer taken a look at? I mean, they're some pretty crazy planets.
There's some pretty crazy planets. You have, well, like I hinted to, you have these HotJupiters that are so close to the planet that they're orbiting that they actually essentially pull up a plasma wave from the surface of the star that as the planet orbits, this wave follows around on the surface of the star. You end up with planets that are essentially leaving behind tails of material as the radiation of the star they're orbiting pushes off the planet's atmosphere. Then you also start finding things that we should have thought about as existing ahead of time, but at least I know I never read about them in journal articles prior to reading about Spitzer observing them. You end up with what we look at as small rocky worlds, but are probably nothing more than the left behind remnants of, well, a gas giant that is a gas giant no more.
That's crazy. Yeah, I mean, some of the most recent observations, right? I was mentioning that, right? That they've turned, or they found objects which are like mini Neptunes that have had the outer layers blasted away and turned into a SuperEarth potentially.
Exactly.
So that's just kind of mayhem. So I mean, how do you get a planet that's in that kind of an extreme environment? How do you get a planet that's so close? I mean, I'm envisioning. I don't know if you've seen these pictures of the rings from Cassini,
yeah,
where you see these little shepherding moons that are moving within the rings, and they're pulling this tidal, almost a gravity wave. They're pulling ice particles towards the moon as it moves around, and then I guess as the moon moves away, then the particles fall back into their place. And I guess that's the same thing, right? That as this planet is going around the star, there is like this super tide that's getting pulled up towards it. How do you get this?
I love it when you ask me questions that if I had a complete answer for, I could say, hand me my Nobel Prize, please. We don't fully know is the answer. And when we first started finding HotJupiters, I remember listening. I unfortunately can't remember his name. It was an Israeli planetary theoretical planet modeler, awesome dude, who was just like, we didn't calculate this to begin with. This was not, to paraphrase horribly, a conversation that occurred in the early 2000s. No one ordered this up. We had kind of assumed the planets mostly form where they are, or they migrate a little bit due to gravitational interactions, but this migrating all the way in toward the sun and stopping. It's the stopping that's the mystification part. So there's various ideas. One of the ones that I like the most, this doesn't mean it's the most likely, it's just the one that there's a whole lot of them out there. We don't know which is right. The one I like the most is you have the sun. It's when it's very young. It's a blasting evil little star screaming in X-rays and other shades of light, and it blasts out the solar nebula around it as part of ending the star formation. So basically you have stuff collapsing, star ignites, star starts giving off light, the light pressure then starts pushing stuff away, so the infall stops. You then have cleared out at least some of the region around the star. Around that you have the solar nebula, stellar nebula, whatever you want to call it. We always call it a solar nebula. And planets are forming in that, and for reasons we can't fully articulate, some of these planets are not pleased to stay where they are, and they start migrating towards that star. And either they stop because they stop absorbing matter and stop having frictional interactions when they hit the inner rim of that planetary disk, and we have no real observational evidence of things clearing a spiral instead of clearing a ring. They stop for some reason. So for some reason, it probably has to do with frictional dynamics. They get dragged in, and then they stop and don't fall in for reasons we don't fully articulate. One of the theories put forward is the sun cleared out that inner region.
Or magic.
Yeah. Something devised in a computer. If you've read Cybermage, magic is mediated by servers. I'm good with that.
And a lot of these planets are also tidally locked to their stars, right? And so they get these ferocious winds that blast across the planet too.
And what's awesome is with Spitzer, they're actually able to get a sense of how wide the atmospheric lines are. And the cool thing with rotating worlds, rotating stars, things that rotate, is as that rotating object, one side of it's going to be coming towards you and being blue shifted, the other side's going to be moving away from you and being red shifted. And of course the middle is moving perpendicular to you, so there's no shift perceived, and this whole rotating body ends up creating a thickening, a broadening of that spectral line, and it gets broader the faster that sucker is spinning, or the faster the winds are blowing, the faster the convective cells in the atmosphere, and we can see that, and we can see, oh dear God, I don't want to be on that world.
That's crazy that you can detect. I know it's awesome, right? That you can detect the speed that it's rotating, the speed of its winds, how long it takes to go around, the composition of its atmosphere, what it's probably made out of based on the atmosphere, and all this kind of stuff without really, as we said, you're not looking at it. You're just having all of these indirect observations based on its spectra, and this is like spectroscopic analysis has got to be just like the greatest tools that astronomers have at their disposal.
It's also the most boring set of images you can possibly
I know, you're just looking at these lines.
I studied magnesium, as I said, I studied magnesium hydride stars, and you can go read the paper. It's in ADS, and that was by far the most boring thing I've done in my entire life. And I study variable stars.
Right. That's why it's a little brighter. Now it's a little dimmer. Now it's a little brighter.
Right.
Now it's a little dimmer. Yeah.
So what's awesome about this is beyond just being able to say, wow, that world has really fast convective cells in its atmosphere. We can also say, wow, that planet, we can start to see water. We can start to see, we haven't yet found free oxygen in an atmosphere. But this has actually led to a whole body of research on what chemical composition, what chemical fingerprint in an atmosphere means there's life. And I actually have a bet with Seth Shostak, who periodically forgets we had this bet because it was over dinner, and there may not have only been food consumed. But Seth Shostak from the SETI Institute and I have a bet on, I say we're going to find life on other worlds first by detecting the chemical composition in a world's atmosphere rather than by detecting radio waves. Love the Allen telescope. It does more science than just listening for little green dudes, but I really believe it's in telescopes like Spitzer that we're going to find life on other planets.
And you and I, we're in complete agreement, and this is why we have advocated for literally the entire time that we have been doing Astronomy Cast together, that there should be some kind of super powerful telescope designed to observe the atmospheres of distant worlds.
Yeah.
Build this telescope, answer the question. Don't you want to know the answer to this question? Just build us a telescope, please.
And James Webb Space Telescope will have the capacity to go beyond what Spitzer's doing and do the job better with a bigger
next,
mirror.
Yeah, so let's talk about James Webb. That's the next, it's going. I mean, with Spitzer, there haven't been a lot of observations, right? There haven't been a lot of planets they've really been able to observe with Spitzer. James Webb is going to take us to the next. It's not like Kepler delivering thousands and thousands of planets,
Kepler's
right?
a discover the planets mission. Spitzer is a follow-up on just the right ones and get extraordinary amounts of data. So the way to think of it is going along and identifying with a metal detector where all of the bits of metal on the beach are and dropping a little piece of plastic saying, hey, there's a piece of metal here. And then where the biggest pieces of metal are, someone else comes along and digs up, Blackbeard's treasure. I don't know.
Yeah, exactly. So let's talk about James Webb and maybe some other methodologies that can use this technique to find the same thing.
So with Spitzer Space Telescope, it's a 0.85 meter, a 2-foot 9-inch mirror. So that's a fairly small. 2 foot 9 inches. Yeah, it's like this.
2.5 feet. Yeah.
Yeah, it's not big. My hair is probably about that length. So with the James Webb Space Telescope, you're looking at a multi-meter mirror that you and I could probably, the two of us, manage to span across. That's a bit bigger. And
it's a gigantic. There's great. Have you ever seen the model?
Yes, I saw it with you. We were both there together.
Right. I always forget. That's right. We were there together at the model, and it was gigantic.
Yeah. So when we were at South by Southwest a couple of years ago, and we posted a bunch of photos of it.
That's right.
Sorry, I had to make fun of you.
Yeah.
If you go see, as Fraser and I have done together
as a team,
the James Webb Space Telescope is big. It's slated to be. I'm looking up the number. It changed size at one point, and I want to not lie about how big it currently is slated to be. And I was going to, so I'm glad I looked up the number. It's currently slated to be 6.5 meters across, and I believe that number will actually stick.
So Hubble is 3 meters? No, 1.6 meters? 2 meters. It's around that area.
Right.
Hubble.
So this is substantially bigger.
Bigger, yeah, and bigger means better.
Yeah, something bigger. Like that.
So that math sort of holds. Yeah.
So in this case, the bigger means better actually does apply. It doesn't always apply. HARPS is on a small telescope. It does awesome work. But with James Webb, it takes what Spitzer's able to do with a small mirror and goes, hey, we can see fainter stuff, which means that they can look at the same stars but at a greater distance and increase the number of stars that we're going to be able to see and detect the planets on. Yeah. So you still have the problem of the planet needs to be transiting. You still have the problem of the planet needs to be hot enough and you don't have a coronagraph. But the number of things that you're able to now look at because you can see fainter objects, which means you can see things that are further away, it's going to increase our sample size. It's going to increase the number of things we're able to look at. It has that spectrograph on board. I believe it's of a higher resolution. Truth will be in the pudding once the sucker's launched and hopefully deploys correctly. It better deploy correctly. But this is, both Spitzer and James Webb Space Telescope are telescopes that in the long history of instruments like Hubble and ground-based instruments like Palomar even, these are systems that are designed to answer a myriad of fundamental questions. Hubble was put up to help figure out the expansion rate of the universe and what the heck planetary nebula are, as well as many other things. But planetary nebula was a real problem when Hubble launched. We just couldn't understand them.
Still don't have that fully figured out either. But
we're a lot closer.
Yeah.
James Webb Space Telescope is going to help us get back to the beginning of the universe when it comes to looking at galaxies forming, but it's also going to help us with the nearby universe, helping us understand the formation of planets, the atmospheres of planets, and when I say planets, I finally get to mean things more than a few light years away.
Yeah, James Webb. Are there any potential ground-based observatories that are going to do this work as well?
Well, what you start to run into with ground-based is as you look further and further into the infrared, our atmosphere becomes a insert all the expletives.
Right.
We have
an opaque wall.
Yeah, we have these evil things known as water molecules in our atmosphere, and it gets a little bit easier when you get into the high-altitude deserts where most of the moisture in the atmosphere is below you and not actually there because you're in the desert. Mm-hmm. Even in Hawaii, though, at high altitude where you're looking down at oceans and clouds, even there it's substantially better, but it's still there. So you really have to be up in space, just like Spitzer. Problem with space is you eventually run out of helium, and you do require helium cooling on these systems. But there are long-term missions you can do just by blocking the light, and James Webb has that amazing and weird solar shield, and when it deploys, it will keep everything in shadow and hopefully keep everything cool.
But they're going to be busy with James Webb's going to be busy, so don't count on it being able to spend a lot of time looking at planets. It's got that whole look back to the very edge of the observable universe job as well. So
dark energy, dark matter, dark planets,
protoplanets.
Yeah.
Peering through gas and dust to see the center of the galaxy. Yeah, it's got some jobs to do. So
but
looking for asteroids, cold Kuiper Belt objects, finding more planets in the solar system. Anyway, James Webb's going to be busy.
Oh,
take a number.
Yeah, but hopefully, like Hubble, it will live long enough that eventually we'll start being able to do the science because there's something bigger and better on the horizon.
Right. And so really, what we're saying is someone should build a coronagraph-equipped infrared telescope.
We'll take a 3-meter.
Capable of analyzing the atmospheres of distant worlds. Put that in the hands of Pamela, and we will find your aliens. Okay.
And I will find an actual infrared observer to do all of the work.
Yeah, no, that person will find it.
I'll just fill out the paperwork.
We will deliver you aliens, okay? We will deliver you aliens. Do you not want to know if there are aliens?
Or at least trees. Or at least trees. We can find the Ents out there.
Yeah,
if there's Ent, we can see it. Or at least we can see the oxygen.
All right, well then, even if we don't get our telescope, we'll see you next week.
Sounds good, Fraser.
Thanks, Pamela. This is how this is going to have to go. We're just going to have to nag people until they build us the terrestrial planet finder. I don't mind. I really don't. I'm ready.
Okay.
Going anywhere?
Not going anywhere. Actually, I'm going to grab hot water.
Not you. You're stuck. I'm talking about everybody else who might want to leave.
I was out at the ASP over the weekend, and Astronomical Society of the Pacific, and that meant I was on aircraft. And being on aircraft means I now have the sniffles and need hot tea. And you are totally muted.
Yeah, I know. I did that on purpose.
Okay.
I was having conversations with other people.
Yeah, I guessed that by the moving lips and the utter silence.
Okay, cool. So let's hammer through some questions here. Richard Clark asks, what is the life expectancy of the Spitzer telescope, and is there going to be a replacement for it when it expires?
No planned replacement. I'm not sure. They keep moving the expiration date, which I'm totally in favor of, but it makes answering these questions difficult.
Well, we know what's going to cause it to go to die, finally.
Gyroscopes or converse. Pick one.
Yep. Gyroscopes.
Well, so we now know from WISE that Congress will actually say you're done to a space telescope that's still completely functional. So we do have to really worry about these older missions getting congressional decommissioning.
I don't see any gyroscopes on Spitzer, so I'm worried for it. I might not even use them. Okay. Let's see. Let's move on. Adam Synergy asks, astronomers will be hoping to use James WST in the future to characterize planetary atmospheres, but it's likely will be much in demand, which we mentioned, and these kinds of observations will be time-consuming. Are the plans for a dedicated infrared space-based exotelescope? Like some kind of terrestrial planet-finding telescope, maybe? Man, I gotta just drop this, don't I? Like a grinding metal at this point.
You need to go to like the Hill in the United States and say, I'm Canadian, but I
Canadian. Care. Like they'll just usher me off. Like, you Canadian, back to the border.
Canada has a space program.
We
mostly.
do. We have one of the most productive little telescopes you can have, pound for pound, dollar for dollar.
Well, and you also have the highest astronomy publication rate in the world. So really, Canada's kind of astronomically awesome. You just don't spend money on facilities the way we do, which means you have money for scientists to do science. Go figure.
There we go. We have the most arms, the most robotic arms. Okay. Let's move on. So yeah, any plans for an infrared space-based exotelescope?
Not that I know of.
It's a great idea. It should happen.
Funding?
Was it in anything like that in the decadal survey?
Not that I know of.
Did scientists even ask for it?
I think the decadal survey really was focused on dark matter, dark energy.
Yeah. Well, then they get what they asked for.
There's another decade coming up. That's the nice thing about decades.
Is it already that time again? Is it already decade time again?
I know that we usually start the decadal surveys 2 or 3 years ahead, so I'm suspecting right after the U.S. solar eclipse in 2017 that we shall all be enjoined into panels.
Right. Skeltandrid asks, Pamela, how many fish tanks are there in your place?
Oh, God. So I was waiting for someone to say something. We had a minor fish tank explosion or bloom, I guess, at Christmas. The little guy over there, it's 2 gallons. I asked for that for my birthday. And my husband got me the 2 gallons, and he bought himself its big brother, the 5-gallon, and he decided the 5-gallon is awesome. And he bought me the 5-gallon, which is right there, because he wanted me to have an awesome 5-gallon too. And then if any of you follow me on Facebook, you know about the Christmas Day massacre that occurred when the beta, which is now banished to the tank up there, decided to start consuming its tank mates. So we have awesome friendly fish, bastard evil tank mate eating, but very, very pretty fish.
I know how your husband's brain operates. We have only begun down the road of bigger and bigger aquariums.
Yeah.
If your husband liked the fish, likes the 5-gallon tank, he takes this to extremes. I imagine 40-gallon, 100-gallon saltwater tanks.
So these are the
tanks
that are in my office, which is the smallest room in the house. My husband, who I love dearly, is a collector of many things. In his office, he has the matching 5-gallon to my 5-gallon, and he has 2 7-gallons, and he has a 20-gallon.
Ah, okay, right.
So, and there's going to be
he's bookmarked 40-gallon tanks.
No, we're going to jump straight to 60. We've had that discussion because he wants to get angelfish. So there will be a
saltwater, right?
No, well, he wants salt water.
See?
I'm the person who's had tanks for a long time, and I'm currently vetoing the salt water until we've been doing this for at least a year.
I can run a simulation of, like I said, of your husband's behavior in my mind, and I had already gamed this out. So we will reach, peak tankitude at some point with a koi pond.
You know, that would be ironic because when we bought our house, there was the infrastructure for a koi pond, and I was like, no. And so I turned the infrastructure to the koi pond into a fire pit. So we replaced water with fire, as one does.
Just saying. I'm just saying. This is the dark future I see for you. 60-gallon tank is just the beginning.
Luckily, we live in a really old house, and our floor can't really support the weight.
That's why you got to take it outside. You got to build a enormous machine outside.
Don't say that.
To support fish.
Our hot tub will turn into a koi pond.
Yeah, exactly. Okay, hold on. Someone wants to call me on the phone now. Let's see if my daughter will grab the phone.
Mute,
That's
mute,
Dad.
mute, 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 mute. You don't want your dad's phone number on the internet. Mute. I'm. Sorry, internet. I like Fraser, and I've only heard good things about his dad. Therefore, we're going to mute his father's voicemail and phone number.
Everybody. Okay. Nancy Graziano says aquarium envy, telescope envy, same size, flip sides of the same coin, right? That's totally true. That is absolutely true.
But you can aquascape a fish tank. You can't aquascape a telescope. You can, however, subject a telescope to very cold weather, and if you do that to a fish tank, they will die.
Fred Miller says, where will we be 10 years from now in analyzing exoplanets?
Oh, God. So 10 years ago, 2005, we were to the point of, we're starting to see transits everywhere. And that was the point where it was starting to become an amateur hobby to start finding transiting planets. 10 years from now, I suspect that with big data, we're going to have people crawling through databases looking for transits that got missed and putting together surveys.
Fred Miller asks, and what are the molecules that would reveal aliens to us?
There's a whole bunch of different things that you look for that are chemically out of balance. So it's not that you generally look for just one thing. It's generally you look for, like, methane being out of balance with the amount of ultraviolet radiation, which is oddly something that is happening on both Titan and apparently Mars. But other things can cause that. The real censures, if you start to see things that can't exist unbonded for very long unless they're constantly getting reproduced, and free oxygen is one of those.
Yeah.
If you have O2 in the atmosphere that has not yet decided to join up with an H, you're pretty likely that you have something like life that is creating that oxygen.
Yeah, we actually did an episode of The Guide to Space based on what Nicole Gallucci had just said offhand. She at one point had said, like, I don't know why people are so worried about broadcasting signals out into space. We've been broadcasting our existence for 200 million years, right? Since oxygen started forming in large quantities in the atmosphere, any alien with a good enough telescope could say, there's life there.
And
send
before that,
probes.
we had methane.
Yeah. Send the robot probes. Scour that place of life. So they haven't arrived, therefore there is no life out there. Or
gamma ray bursts ate them. That's one of the new interesting papers that just came out, was it could be that the frequency of gamma ray bursts is such that civilizations start to hit the I shall go forth, and then a gamma ray goes, no, I shall smite you.
Yep. Whap. So, okay, I got like one more minute, and then I know my dad is getting a table at the restaurant and glower at me. Ranko Proza wants to know, will there be another CosmoQuest fundraiser this year? Oh, God, yes. I should have the date to announce next week. Oh, God, yes. It will be 36 hours again, and I'm proud to say Celestron has already said they're going to be one of our sponsors. Right on! Good job, Celestron. So, yes. The folks at Celestron are awesome, and they're also supporting the 365 Days of Astronomy podcast for the International Year of Light. One more. Michael Meyer asks, could you find intelligent life with a spectrograph? Yes. You'd look for their pollution, look for their chlorofluorocarbons, right? Yes, yes. In fact, we could tell almost exactly what level of technology they have based on what we see in the atmosphere with a good enough spectrograph.
The problem is if they're responsible aliens who have stopped destroying their planet, can't see them.
Yeah. How would that even exist?
Whales, advanced whale societies.
Yeah. Cool. Okay, well, let's wrap this up. So, hey, thanks everybody for watching. Thanks, Pamela, once again for regaling us with your brain. We will see all of you next week. Don't forget to listen to the Learning Space Wednesday, next Learning Space.
And go donate to Fraser's Patreon for Universe Today and
Learning Space's Patreon for Learning Space.
Yes.
Awesome. All right. Well, we'll see you next week, Pamela. We'll see anyone who wants to show up on Friday when we talk to Paul Glister from Centauri Dreams. And we'll see you all next week.
Sounds great, Fraser.